In this video, we're going to talk about the null and alternative hypotheses. So we are entering the chapter on hypothesis testing. And we're going to kind of talk about one specific type of hypothesis test. And then if you move on in statistics, you would actually learn that there's a lot of different hypothesis tests. So from science, most people are aware that a hypothesis is an educated guess. So this is kind of the science part of statistics. If you might remember, the definition of statistics is that it is a science. So when we do a hypothesis test, we kind of follow some basic outline here. You would start by setting up two contradictory hypotheses. And then you would collect sample data. Now, we're not going to do that. They're going to collect the data for us and we're going to analyze that data. But that's kind of one of the steps you would do. So you're going to determine the correct distribution. Now, when there are multiple hypothesis tests, you have to know which distribution to use. We only know one distribution. That's the normal distribution, the bell-shaped curve. And so our hypothesis test is going to use the normal distribution. Then you're going to analyze the sample data. And from there, you're going to make a decision and write a meaningful conclusion. All right, so let's kind of get into this. How do we actually write two contradictory hypotheses? So we call these hypotheses the null hypothesis and the alternative hypothesis. So the null hypothesis, we use H sub 0 to represent. I actually, when I first heard this, my teacher called it H naught, using like the British version of sub 0, H naught. So if I slip into calling it that, sorry. So the null hypothesis is the statement we're going to be testing. And the truth is, the null hypothesis is kind of everything. It's the thing we'll refer to also when we write conclusions. So the null hypothesis is kind of the big important step here. The alternative hypothesis, and some books might use H sub 1, but our book uses H sub A for alternative. Okay. This is the alternative hypothesis. And the alternative hypothesis is a claim that's contradictory to the null hypothesis. Okay. And it's also the thing that we're usually trying to find evidence to support. So in a lot of examples, the null hypothesis is like the known belief, the starting point. And then the alternative hypothesis, I just realized I forgot to write the word hypothesis, is an alternative to that. So we often look for evidence to support the alternative hypothesis. That is not always the case. You're going to kind of see based on the way we set it up how we kind of word these. Um, but it is important that they're contradictory in nature, and we will set them up that way. So um the types of statements we're going to have for the null hypothesis is we're going to be working with a comparison of a population parameter, and we've talked about parameter. A parameter is some sort of numerical measurement, okay, like the mean or a proportion or the population standard deviation. Now, we are only going to use the mean just because we're starting off and kind of learning what hypothesis testing is, but there are variations on hypothesis tests that use all three. Okay, so our null hypothesis is going to be a parameter, whichever one we're working with, more likely mu, well, not more likely, it will be mu for us, but it'll be parameter is going to equal some number. I'm going to use the hashtag symbol, but that originally was the number symbol before it got co-opted, all right, onto social media. For math people, that means number. Now, one version of an alternative hypothesis could be saying that the parameter does not equal that number, just flat out doesn't equal that number. See how they're contradictory to each other? If one is true, the other can't be true. All right. We call this a two-tailed test. Sorry, that kind of looks similar to each other. Let me make it a little bit clearer that that's the number symbol. I don't think that was all that much clearer. Oh, well, it's a two-tailed test. And that's talking about the graph, which we'll look at later on. So another type of alternative hypothesis. So it's still for all of these, for simplicity, we're going to let the null hypothesis always just be equal to some number, some value. All right. The alternative is what's going to change. So in this case, let's say the parameter is that it is smaller than that value. Again, they can't both be true. They contradict each other. So if one says they're equal, the other says that one is less than, that can't be, they can't both be true. In this case, this is going to be a left-tailed test. We'll come back to that. And lastly, perhaps our parameter equals some value. And the alternative would maybe be that it is greater than that value, which is a right-tailed test. All right. So for simplicity, we're going to kind of take that approach. Some books do allow the null hypothesis to take on an inequality. But yeah, we'll kind of keep it simple and make it easy so that we don't have to stress about that kind of scenario. All right, so let's go ahead and look at some examples and we'll write the null and alternative hypotheses for them. We want to test whether the mean GPA of students in American colleges is different from 2.0, and this is out of 4.0. So let's state the null and alternative hypotheses. So the null hypothesis is always equal. And in this case, they're talking about a mean. So I'm going to use mu because we're talking about the population parameter. And the claim is that it's different from 2.0. So the null hypothesis is going to assume it equals 2.0. And the alternative is going to then be that it's different or not equal to 2.0. So being different, we typically mean that or think that to be not equal. We want to test if college students take less than 5 years to graduate on average. So average again, okay? So we're looking at mean. So since they're interested in 5 years and it being less than 5 years, that's going to be our alternative hypothesis. So our null hypothesis is always going to be the equals. So the mean is going to equal 5 years, but the alternative would be less than 5 years. In an issue of the U.S. News and World Report, an article on school standards stated that about half the students in France, Germany, and Israel take advanced placement exams and a third pass. The same article states that 6.6% of U.S. students take advanced placement exam and 4.4% pass test. If the percentage of U.S. students who take the advanced placement exams is more than 6.6%. Okay, so different parameter. We're actually talking about percentages. So this is a proportion. So I'm going to use P this time. And they want to know if the advanced placement exams is more than 6.6%. So P is going to equal 6.6. But I'm going to actually write it in decimal form because when we work with the number, we want it as a decimal, not a percent. So it's smart to go ahead and write it as a decimal. You could write it as a percent, but we'll stick to decimal form. So then the alternative is that it's going to be more than 6.6% or 0.066. Okay, so that's all null and alternative hypotheses. That's kind of what you'll be looking at. I did want to talk about errors in hypothesis testing. So we have a couple of important things we need to keep track of when we're doing a hypothesis test. So I kind of created this little table here for us to fill in. And here's what we're going to put. We have 2 actions in our hypothesis tests. We will either reject the null hypothesis or not reject the null hypothesis? Okay. So we'll have those kind of two basic ideas. So reject or do not reject. And that's kind of how we're going to even word our conclusions too when we get to that point. So if we were God and we actually know a couple of important facts, in other words, if we know that the null hypothesis is true, okay, then you wouldn't want to reject the null hypothesis, right? If you happen to know that, like, we have this vision and understand how everything works and we're all knowing, the null hypothesis is true. The correct conclusion would be to not reject. So if we rejected the null hypothesis when the null hypothesis is true, that's a type of error. And the error we call that is type 1. The other possibility is that the null hypothesis is false, or the alternative is true. In this case, if the null hypothesis is false, you would want to reject the null, saying that it's wrong. Okay. So this would be the correct conclusion. But if you don't do that, if you choose not to reject the null hypothesis, that would be another type of error, and it's a type 2 error. Okay. So I want to kind of equate this to an idea that most people understand, and that is our justice system. In our justice system, we say that a person is guilty or not guilty. Notice that we don't say innocent, right? We say guilty or not guilty. When somebody is guilty, we say that beyond a reasonable shadow of a doubt, right? Beyond reasonable doubt, we believe they're guilty. There's plenty of evidence to support their guilt. And if we have doubt or we don't believe there's enough evidence, we would say not guilty. Okay, so we have to kind of ask ourselves which is worse, to let a guilty person go free or to send an innocent person to jail. And the truth is, in our justice system, we believe it's far worse to send an innocent person to jail than to let a guilty person go free, mainly because often somebody who's guilty or is a criminal, they'll often commit another crime. So we might get them later. But an innocent person being convicted of a crime is a very big deal. So in this scenario, an innocent person being called guilty is a type 1 error. So this is the more serious of the two errors. We want to avoid type 1 error. And in fact, the whole hypothesis testing system is set up to minimize type 1 error. In type 2 error, when we don't reject the null, what we're basically going to say is that there's just not enough evidence. And it almost in that statement implies that maybe it is wrong, but we just didn't get the evidence enough to do that. Okay, so now that we kind of understand that, they kind of sum up what I just said here in these 4 possible outcomes. And just to make it very clear, the type 1 error is the most serious of the two. So this is the one that we really don't want to commit. And it is the one we are trying very hard to minimize. We do have some labels for this. We use the Greek letters alpha and beta. Alpha is going to represent the probability of a type 1 error. My alpha slightly looks like a 2. Sorry. I'm not going to try to erase it because I'll probably mess it up. And beta is the probability of a type 2 error. Now, we've already seen alpha notation when we did confidence intervals. That's not a coincidence. That's on purpose. Okay. This is the same alpha. Alpha is the chance that we're wrong. And when we're talking about hypothesis testing, it's referring to the chance that we make a type 1 error. And therefore, we are constantly trying to minimize alpha. We're trying to make sure alpha is very small. And therefore, we want to make certain that we are minimizing that error. Okay, so let's kind of write what a type 1 and type 2 error look like for this particular example. Frank's rock climbing equipment is safe. Now, this isn't a standard null hypothesis because it's more of a statement, but it makes it a little bit easier to do type 1 and type 2 errors. So, a type 1 error here is going to say, let's come back up here. Look at our board here. It's when we would reject the null hypothesis, even though it's true. So we would reject that his rock climbing equipment is safe, but it is. So Frank thinks, oops, that's supposed to be an N. Frank thinks that his rock climbing equipment is not safe, but it is. So the last part of the statement is the part that tells us what the actual truth is. Okay, so a type 2 error, come back up to our table. Type 2 is when we do not reject the null, even though the null is false. So in this case, we would say that Frank thinks his rock climbing equipment is safe, when in fact it isn't. Now you gotta love that the book picked this example when I was just trying to emphasize that the worst error is type 1, but this makes it sound like it's type 2. Oh, sorry, it is not safe. Yeah. All right, thanks. But for most part, it doesn't end up kind of looking like this. It usually ends up being worse because often what we'll be looking at for hypothesis testing is like maybe a claim that a company makes. And if we think the company's wrong and we say that, we better know we're right because most companies are going to sue you or come after you if they think that there's anything wrong with what you're saying. Okay. Um, but yes, in this particular example, it would be worse to do a type 2 error. And I think they actually state that down here. Yes, they do. But this is rare. I'm going to say that. It's rare. And kind of wish they had picked a better example for that.